I started recording on my own.
Oh,
I'll just
okay,
send you the
very good.
link then.
That's fine. Okay.
Okay.
So, all right. So you should now be able to see my slides. Is that correct? Yeah. Mhm. Right. Okay. So today I'm going to talk about a project that we've been working on for several years. And this project is about modeling individual differences in sentence processing. The work is actually led by Himanshu Yadav, who's actually present here. He's maybe doesn't have his camera on, but he's a PhD student of mine, and he's the lead person on this. And Dario Papa and Garrett Smith are postdocs in my lab, and they're collaborating with us on this project. Brian Dillon has been involved for many years in these discussions with me about individual differences. Okay, so that's why he's a co-author here. So these are many of the other people who are involved in this project. So this is Himanshu here. And a lot of the experimental work was done by Lena Jaeger, who's a professor in Zurich now, and in collaboration with Van Dyke, Julie Van Dyke. These are the two guys, Garrett Smith and Dario Papa, who are collaborating on this project. Felix Engelmann was my lead programmer and lead model developer. I will just tell you more about that. And there's some more experimental work that Daniela Mertzen has done. So these people deserve a lot of credit, for a lot of the behind the scenes work that led to this final project. There's a lot of many years of work that I had to go into preparing ourselves empirically to get to the point that I am at now. Okay? So if you are interested in looking at the computational modeling work that we have been doing, all of this material is available with code and data from my homepage. So you can download everything that we have published along with the source code and the original data that we used for modeling. And the actual computational model that we're going to be talking about today is available from Felix Engelmann's GitHub repository. Okay, so another thing I want to mention is that I've just recently finished a book that was funded by the Volkswagen Stiftung, which summarized about 20 years of work on this computational modeling and sentence processing that we've been doing. And so this work basically summarizes the entire big picture behind today's talk, right? So I'm not going to discuss all of this stuff, but it's all there if you want to look at it. And of course, the source code is all downloadable from this website here, right? Okay, so the computational model that lies behind the story today is something that I'll call the activation model of retrieval processes in sentence processing. So this is a very long name, so I'm going to give it a shorter name. I'll just call it the Lewis and Vasisht model, because this model is based on a 2005 paper that my advisor Rick Lewis and I published in Cognitive Science. And since then, we've been developing this model in different directions, right? So I just call it the Lewis and Vasisht model. And these are like three major papers that summarize the latest developments, the original paper, and then the latest developments in the modeling, right? If you want to read these papers, you can download them from my homepage. So today, I'm going to talk about one particular set of predictions from the model. So there's a very interesting prediction that the model makes, and the prediction is the following. Right, so if you look at the first sentence here, 1A, this sentence is actually ungrammatical. Okay, the bodybuilder who worked with the trainers were complaining, blah blah blah. The sentence continues, right? The sentence is ungrammatical. Why? Because bodybuilder is singular, the auxiliary verb is plural, right? That's not a grammatical sentence of English. However, it turns out that people actually don't notice the ungrammaticality in this sentence often. And people often produce sentences like this. Even when I'm writing papers about this topic, I even produce sentences in the paper that has this kind of construction. So what's happening here is something called agreement retraction. This auxiliary verb is plural marked. There's a distractor noun inside a prepositional phrase here, which is not the subject of the auxiliary, but is plural. And this local agreement of the noun and the verb, this has the weird effect of giving you an illusion of grammaticality, Okay, so you end up thinking, oh yeah, this sentence is fine. And you notice the contrast if you compare it with a baseline sentence where the subject noun is still singular, just like here, and the auxiliary verb is plural, but the distractor is singular now. Now, if you read the sentence, you will feel the hit. You'll feel that the sentence is really bad, right? The bodybuilder who worked with the trainer were complaining. That feels really horrible. But this sentence doesn't seem so horrible, actually, right? And so that's a very interesting and fascinating issue. Why do people find the first sentence better than the second sentence, even though both are equally ungrammatical, right? So this has been studied intensively in many languages, and it's a very robust phenomenon. And what we notice in reading studies, if you do eye tracking studies and so on, you notice that people read this auxiliary verb in condition 1A faster than in condition 1B. So they somehow find it easier to read this verb auxiliary than this verb auxiliary, right? And this has something to do with this local agreement here, right? So we will call this speed up in reading in A versus B. We'll call it facilitatory interference for reasons that I will just explain. Okay? So what's happening here? So the theory is that the reason people find the auxiliary easier to read in 1A versus 1B is that there is a search that is initiated at the auxiliary for a noun that is the subject of the sentence and that is plural marked. So there are two features that the system is using at the auxiliary to seek out the correct target for retrieval, for building a dependency between the subject and the verb. Right, so there's two features, subject and plural. The subject feature matches the subject of the sentence, but the plural feature doesn't match the subject of the sentence, it matches the distractor. And so you end up in this weird situation here that one retrieval cue is pointing to the subject and the other retrieval cue is pointing to the distractor noun. And this is what this does is that it will occasionally cause, because of the partial feature match of the plurality feature between the auxiliary and the distractor noun, you will occasionally retrieve the distractor noun as the subject of the sentence. So you misretrieve the subject. You think that trainers is the subject of the sentence. Okay. And when you do that, you think, oh yeah, this sentence is fine. Everything's good, right? This sentence is dramatic. So this is what we call facilitatory interference. The distractor noun interferes with the retrieval of the subject, and you end up retrieving the wrong thing. And this leads to a speed up, yeah, at the verb compared to this baseline condition where there is no plural distractor noun, right? So in the second condition here, 1b, you're still looking for a subject that is plural marked, but you get a partial match with the subject. But you don't get any noun in the sentence that is plural marked. So you don't get a partial match with the plural. So you have more difficulty retrieving the subject. And you realize that there is a problem here because you notice the absence of agreement, right, between the two. So that's the explanation from the Lewis-Physich model for the speed up at the auxiliary compared to this condition here. All right, so what's interesting now is that the same type of speed up should occur in an antecedent reflexive condition. Okay, so now consider sentence 2a. The bodybuilder who worked with the trainers injured themselves. Right? Themselves is plural marked. It's looking for something like a subject. It's looking for a C commanding antecedent. So I'm calling it C command here now. So the same situation holds as before. You've got two features that are being used for retrieving the subject, and that's also happening here. And one feature, the plural feature, is matching the distractor noun again, right? So the expectation is that in these two sentences, we should see a speed up at the reflexive in 2a versus 2b for exactly the same reasons that we see the speed up in the auxiliary in 1a versus 1b. Is this clear? That's the prediction. Okay. Now, what's interesting is that this prediction about the auxiliaries, the subject verb, agreement that we have here, this is very well validated in the literature. We repeatedly see speed ups here versus here. The interesting situation is the reflexive here. Here we see some really peculiar data that is difficult to explain. Okay, so what we found was that Brian Dillon published a paper in 2013 in one of our top-ranking journals, the Journal of Memory and Language, in which he showed that in condition 2A versus 2B, there is no speed up observed at themselves, right? So this is counter to the predictions of the Lewis Vassation model. And so Dillon argued that reflexives are actually somehow exempted from interference effects. They do not suffer from the same distractor effect from this distractor noun that the auxiliary verb suffers from. So there's something really different between the subject verb dependency and the antecedent reflexive dependency. That was his proposal. And it was actually based on earlier work by Patrick Sturt and other people, right? So this is an old idea, but Brian Dillon was the first one to directly compare the auxiliary subject verb auxiliary relationship and the reflexive relationship. And he showed an asymmetry, in the patterns. In the auxiliaries, we see a speed up in 1A versus 1B, but in the reflexives, we don't see anything, right? So the question is why? Okay, why is it that reflexives are special and they are not, they do not suffer the facilitatory interference effect? Why is that, right? That's the interesting mystery. So Dillon's argument was the following. Okay, again, this is based on Patrick Sturt's work, but his argument was that reflexives are special because the antecedent reflexive relationship is determined by principle A of the binding theory. And principle A of the binding theory is a very, very special principle. It's a very special constraint in language, right? And it's such a strong constraint that no amount of distracting, feature matches with a distractor are going to impact that dependency completion. Once the system knows that it has to find something using principle A, nothing can distract the system from finding the antecedent, right? So the way he expressed this idea was that the C command Q, this Q, has a stronger weighting than the plurality queue, right? So you can imagine that you can put different weights on different queues, and if you increase the weighting on one queue, the other queue doesn't have any impact anymore, right? That was the idea. Right? The higher queue weighting leads to immunity from interference in reflexives. This was the proposal. And so what do the data look like? Let me now show you what the empirical data look like. Okay? So first, we are going to look at the triangles. Just focus your mind on these two triangles here. First, we are looking at the data from Dillon. This is the Dillon data. What you're looking at is the difference between condition 1A and 1B. Remember? We are looking at the difference in reading time in 1A versus 1B here. Okay, that's what I'm showing you. That's this number here. It's about minus 60 milliseconds or so. And this is a 95% Bayesian credible interval. So this is telling you the range of uncertainty of that estimate given the data, right, for that effect. So you can see that this is a speed up, right? It's a negative number. So it's a facilitatory interference effect. We see that in the agreement dependency, but in the reflexive dependency, right, in the Dillon data, we see a number, a mean that is close to zero. And I mean, it has some uncertainty around that, right? So the interesting thing for Dillon was that you've got a negative facilitatory interference effect in agreement, but you don't see any evidence for an interference effect in reflexives, right? And it's this difference that is a puzzle for him. Okay, this was the puzzle for him. So, so what happened was that when I saw this result, I was kind of skeptical of this result. And the reason I was skeptical was that the sample size of the study was 40. And I know from my own research on sentence processing that this sample size is way too small to accurately detect the true effect in the data. So what we did was we reran this experiment over 4 years. We reran this experiment using Dillon's items with 181 subjects. Why 181 subjects? The reason was that we ran out of time. After 4 years, we just got exhausted, collecting data. So we decided, okay, we're going to stop now. Okay, but that's the best we could do. And we compared the estimates from the Dillon data with our own data. So you can see that my credible intervals, these squares here are my estimates, okay? you can see that my estimates of uncertainty are much smaller now. That estimate is smaller because my sample size is much larger. Okay. So what you should notice now is that the two estimates are very similar now. They are both showing facilitatory interference effects. This is very different. This conclusion is very different from the conclusion that Dylan got, right? And so there's a fascinating backstory here about why low sample size will tend to give you such divergent, estimates. I can tell you about that if you want to know, but that's not the main point of the talk. The main point of my talk today is that there is a difference in our findings, that for large sample sizes, we see no difference between the agreement and reflexive conditions, but Dylan found this difference, okay? So I wanted to explore this issue a little bit more for the following reason, right? So one interesting thing to think about in psycholinguistics is that the way we do psycholinguistics, and this is true in linguistics as well, right? Anyone who does empirical work in cognitive psychology, psycholinguistics, regular linguistics, what they do is that they compare the average of two conditions. We always compare the average over all the subjects data and all the items data of two conditions, right? So if I'm talking about, the way I was talking about this phenomenon was I've got these two sentences here, and I will look at all the data from all subjects and all items for this condition, all subjects and all items for this condition, and compare those two means. Actually, that is what you're looking at here. These are averages that I'm comparing. These are averages here, okay? So what's interesting about that is that that completely misses the whole point of empirical science, because the average is a completely useless number to look at for many, many different reasons. It's a completely useless number to look at, right? So this is not my own insight. This is not my own discovery. There's a very famous Bayesian statistician in Cambridge, David Spiegelhalter. His name is German, but he's British. So he calls himself Spiegelhalter, but because I've lived in Germany so long, I can't bring myself to say Spiegelhalter, actually. I always say Spiegelhalter. Okay. So anyway, so Spiegelhalter has been pointing this out for many, many years, right? He does medical statistics where it is very important, right? If you tell somebody that your risk of death is 5%, what you're being communicated is an average, but that average is completely uninteresting for you as an individual, right? Because that average is conditional on your medical pre-existing conditions, on various other factors, your age, whether you're overweight, et cetera, right? So there are individual differences that are much more relevant and much more realistic for understanding what the risk of death is, right? In medicine, this really matters, right? Giving me an average risk of death is not an interesting thing, okay? So the way that Spiegelhalter has summarized this point is that the average is an abstraction. The reality is variation, right? And so the relevance of this idea for psycholinguistics and related areas like psychology and linguistics is that modeling average effects is never going to give you a realistic understanding of what is actually happening in the data. You will, of course, be capturing something. You will be capturing average differences, but those average differences are missing important details. And I'm going to demonstrate now what important details we are missing out by ignoring the individual level variation here. Okay? So it's a very cool problem. Okay? So what I'm looking at now, what I'm showing you now, is the individual subject's estimates of the facilitatory interference effect in the Dylan experiment, in the reflexives, and in my replication attempt. Sorry, no, so this is all Dylan's data, sorry, in reflexives and in agreement, okay? So these are the 40 subjects. On the y-axis, you've got 40 subjects. I've removed the subject IDs because it's just a distraction. The numbers don't matter, right? What is interesting is on the x-axis, you see the estimate of the interference effect. These dots are the estimates of individual subjects, and the thick bars are 80% credible intervals of the estimates, okay? And the thin bars are the 95% intervals. So what we are seeing here is that some subjects have large agreement attraction effects, so very big negative effects, and some have small effects, and some approach zero. Okay, so this is true in both agreement and in reflexives. So what's interesting to notice here is that there is individual level variation in the magnitude of the interference effect across subjects. And what I want to communicate to you today is that there is actually a systematic explanation for this variation, or there could be a systematic explanation. Okay, so I will propose a theory about that. And this will give us actually new insight. Understanding this systematic variation will give us new insight about the underlying process model that we are studying. The Lewis-Vasist model has some underlying latent processes that we can actually unpack if we think about the individual level variation and why it's happening. Okay? So you will notice that in our large replication attempt, the 181 subjects, we also see this distinctive pattern that I just showed you in the Dillon study. We see the same type of pattern in the large sample study, right? So some subjects have large effects, some subjects have effects closer to zero, right? And the question is why? So, right, I don't know why I repeated this. Sorry, this was, yeah, here we go, right? So what's interesting now is we're going to try and explain the difference in the magnitude of the effect across subjects. So what we can do is we can derive from the Dillon, idea of Q weighting, we can derive the following prediction for individual subjects, right? So the implicit idea in the Dillon proposal was that, just to remind you, the idea was that the C command Q in reflexives has a higher weighting, and therefore subjects do not experience interference from the distractor, right? That was the idea. Now, implicitly, what Dillon is actually saying there is that all subjects are going to show this property, right? All subjects are going to have a higher Q weighting for the C command Q. So what I've written out here is an inference that I've drawn from his proposal that all or at least most subjects should have higher Q weighting for the C command Q than the plurality Q in reflexives. In agreement, according to Dillon's story, in agreement dependencies, most subjects will have equal Q weighting, right? Why is that? Because most subjects are showing because we are seeing a facilitated interference over effect overall, and that must be because all subjects have equal Q weighting, all or most subjects, right? So that's the proposal we're going to test now, right? What is the Q weighting? We are going to estimate each subject's Q weighting from the model, okay? And we're going to find out what the range of variation is in the Q weighting in individual subjects, both in the original Dillon data and in our replication, right? So in order to do this parameter estimation, it's not a trivial thing to do now. Well, the reason is that you're going to have to look at each subject's data, and you're going to have to estimate a bunch of parameters, right? So right now I'm only talking about Q weighting, but the Lewis and Vasist model has other important parameters that we will have to estimate. So as soon as you have to estimate 2 or 3 different parameters at the same time, you're going to hit a computational wall, right? So the conventional way that people do this, do parameter estimation, is that they're going to do something called grid search. This is a very primitive method, right? And the primitive method is you put together all possible combinations of the parameters you want to estimate. You derive the model predictions from those combinations, and you see which one of those parameter combinations ends up close to the observed data. And then you take those parameter estimates as your optimal estimates. It's a very expensive and wasteful procedure, right? And it takes forever to estimate those things, right? So that's one problem. It's computationally expensive. Another problem is that you can't actually compute the uncertainty of your parameter estimate. This is a very important thing for a modeler, right? When I have a parameter estimate that I derive based on data, I want to know how unsure I am of that parameter estimate. That is pure gold, that information for me, right? That tells me how much variation there is going to be in that parameter, because that determines what the range of predictions of the model are, right? And it's very important to understand how much variation there is in the model's predictions, right? So the average is not very interesting. The average prediction is completely uninteresting. It's the range of variation in prediction that's interesting in a model, okay? So parameter uncertainty can't be quantified using this grid search method. So the better approach is to use a Bayesian approach, okay? Because Bayes will always give you an uncertainty on the parameter, right? So it also has the advantage that you will be computationally more efficient. You can quickly get your estimates, relatively quickly, I mean, and and it works. The best part is that you can use the Bayesian approach even if you can't figure out the likelihood function of your model. So in this case, in the present case, this is a very important problem, because the Lewis-Vasish model is actually a very complicated process model. It's not really possible to write down a likelihood function that reflects the Lewis-Vasish model. You can write it down, but you have to simplify the model quite a bit to write down a likelihood function, right? So, and the reason that the Lewis-Vasish model in its original form is so complicated is that it consists of different modules that are interacting with each other. There is an eye movement control system in the Lewis-Vasish model. It's just an independent system of eye movements that simulate reading on the screen. Then there's a button pressing system. There's a simulated hand that presses buttons and carries out different actions, right? These are subsystems in the cognitive framework that we work in, and they're all interacting with each other. Writing down a likelihood function is out of the question here, right? It's a process model with lots of latent processes. So in that situation, what you can do is you can use something called approximate Bayesian computation to estimate the parameters just like you would in a Bayesian analysis, right? So how does that work? So as you probably know, Bayesian parameter estimation, the classical Bayesian parameter estimation works as follows. You've got some likelihood function, right? F, y given theta. Theta are the parameters in the likelihood function. You define some priors on the theta parameter or parameters, right? And then you derive the posterior, that is the probability density functions of the theta given your data y using Bayes rule, right? So this is the Bayes rule that we are using to derive the posterior distribution, right? So this is the classical Bayesian method. And of course, if you know the likelihood function, you're golden. You can just do this. And these days, the state of the art is to use STAN. This is the software that we would use for such kind of work. And we actually do use it for parameter estimation. So this is really easy, right? Estimating the posteriors is now very easy with STAN using regularizing priors and so on. This is all solved problem. But when the likelihood is intractable or unknown, we are going to use approximate Bayesian computation. And how does that work? So actually the idea is superbly simple. It's just unbelievably easy, right? So what you do is you generate a sample from your prior distribution of the parameter. Okay, so I'm going to call that theta tilde. This is a random sample from my prior on theta. Okay. What you then do is you take that random sample of the prior and you stick it into your model, right? And the model will then generate a prediction about the phenomenon you're studying. So in this case, it's facilitatory interference, right? So it will predict a difference between two means, and that's what I'm calling a data point here, right? So the model generates the data point. So then what you do is you compare the generated data with the observed data, and you check if the model generated the data that was close to the observed data or not. If the model generated data that was close to the observed data, you adopt this theta tilde as a sample from the parameter space. If the model generates data that is far away, okay, that's very far away from the observed data, then you reject the sample and then you try again. Okay, so you repeatedly keep generating random data from the prior on the theta, and you adopt the theta if it generates data close to the observed data, right? That's it. That's ABC, right? Everything else is now decoration after this, because there's of course a lot more complicated detail that comes in. Okay, it's not that simple when you start doing serious modeling, but the basic idea is very simple. Okay, so that's it. Once you have enough samples of theta, which I'm calling theta tilde here, you've got the posterior distribution on that parameter, and now you can study the properties of your model using that posterior. So you're done, right? So that's how you would do parameter estimation using ABC. Very cool, right? Okay, so the complication here is that we have repeated measures data. Okay, so in psycholinguistics, we always collect multiple measurements from each subject, and multiple measurements from each item, right? So that repeated measures data means that we have some population level parameters in the model that generates the data, and we have individual level estimates also, right? This is the linear mixed model in action, basically, right? Whenever you analyze repeated measures data, you have to analyze data at the population and individual level because of this hierarchical nature of the data, right? So how to estimate, these population and individual level parameters? Now, there's a method that was developed by Brandon Turner, who's a famous psychologist, and Van Zandt, who's also a famous psychologist at Ohio State. So they developed a great method called hierarchical ABC using Gibbs sampling that can allow you to estimate the parameters even when you have this kind of repeated measures data, right? And so this method is called hierarchical ABC. The details I will not discuss, but Himanshu is there today. You can ask him if you have questions about, is he there right now? I don't know. Himanshu is there, yes. So he will discuss more details if you want to know, and you can talk to him later if you want to. I will not discuss these technical details. I'll show you the end results of this model, okay? So the basic idea is going to be that we will first estimate the individual level parameters and then sample from a conditional distribution, conditional on the participant level parameters. This is a very obscure statement, by the way. If you haven't done, Bayesian modeling, you will have no idea what I'm talking about, okay? But I understand that point. But I did want to give you a high level entry into how this will be done, but the details can be discussed later, okay? All right, so let me go on. So now we're going to test the predictions from the Dillon et al. Account. Okay, so remember what the account was. I derived this prediction from the Dillon account, which was that most subjects should have a higher Q weighting for the subject Q in reflexives, but in agreement, most subjects should have equal Q weighting. That's the prediction I'm going to test now. Okay? So what you're looking at now is the agreement data from Dillon. Okay. So on the x-axis, you're seeing something called Q weighting. You have to understand this Q weighting in the following way. A Q weighting value of 1 means 1-to-1 Q weighting for both Qs, so equal Q weighting. A Q weighting of 4 means that the structural Q, the subject Q or the C command Q, has 4 times higher weighting than the plurality Q, right? So this is a ratio that you're seeing here, right? So high values mean high Q weighting, and a value near 1 means equal Q weighting, sorry, not low Q weighting, but equal Q weighting, right? And for various technical reasons, we are constraining the Q weighting to lie between 1 and 4 because that's a reasonable range, okay? So what you should notice now, and the y-axis is the 40 subjects from the Dillon study. And what you're looking at here, these dots that you're seeing, these are the means of the Q weighting for the 40 subjects estimated using hierarchical ABC. And the uncertainty intervals that you're seeing around them, these are the 95% credible intervals on the Q weighting estimate, right? This is the beauty of Bayes. This is the incredible power of Bayes, that you not only know the estimate for the subject, but you also know how unsure you are of that estimate. This is pure gold because this tells you how vague your prediction is going to be. This will become very relevant very soon, right? How vague is your prediction going to be for each subject, right? Do you have sufficient data to make an accurate prediction? Okay. So what we should notice now, okay, so now we know what this figure looks like. What we notice now is that almost all subjects in the Dillon agreement data, almost all the subjects show a Q weighting of 1 for agreement. This is exactly as Dillon predicted. Okay. And similarly, in the Jaeger et al. Data, so this is my lab's replication attempt of the Dillon study, what we notice is that our 181 subjects, almost all of them are close to 1 also, right? So my conclusion from this figure is that for agreement dependencies, Dillon's prediction for individual subjects is actually correct in both data sets, right? Consistent with the predictions, most subjects have almost equal Q weighting, essentially equal Q weighting. So that is very cool, right? So Dillon was right about this. Now let's see what happens with reflexives, okay? Reflexives are very interesting now. So again, I'm showing you on the x-axis, I'm showing you Q weighting. And on the y-axis, I'm showing the subjects, right? So 40 subjects here, 181 subjects here. What we are now seeing is that some subjects have equal Q weighting. This is not consistent with Dylan's idea, but there are a few subjects who show non-equal Q weighting and show higher Q weighting for the structural Q, right? We see that both in the Dylan data and in the Jaeger data. This is now very interesting, right? Because if you remember, when we looked at the average differences between the conditions, let me remind you, right? If we compare the results from the Dylan data and from our replication attempt, we see very different results, right? For reflexives, we see very different estimates, conclusions here, right? So Dylan is concluding no effect. We are concluding facilitatory interference. That's because we're looking at the average effect. If we look at the underlying differences in the individual level between these two, we see that actually the subjects are showing the same pattern, right? And what is that pattern? The pattern is the following. What we are seeing is that in both data sets, there are a few subjects who show higher Q weighting as predicted by Dylan, but most of the subjects are not showing higher Q weighting. Okay, so now we can speculate. So this is still a speculation, okay? We can speculate as to why some subjects have higher Q weighting and why some subjects have equal Q weighting. There could be a systematic reason for that, right? What's the systematic reason for that? So I'm going to now discuss that, right? So one plausible reason why individuals might have different Q weighting in reflexives could be differences in proficiency. Okay, so we know that different people read with different levels of proficiency. Some subjects are very fast readers and very fluent readers, and some subjects are very slow readers. Okay, this could be a function of many different things. We don't know what the underlying reason might be. It might be, working memory capacity. It might be just experience, just exposure, right? So we don't know the underlying cause, but there are differences in proficiency, right? So we can operationalize proficiency via reading speed, right? For each subject, we can measure the reading speed and classify its subject as proficient or non-proficient, right? So in the Lewis and Vasist model, this is what I'm calling LVO5, proficiency is actually modeled as a parameter, which is called a latency factor inside the model. The details I won't discuss because I would have to go into my model's details and that would take 1 hour, so it just takes too long. But basically you have to trust me that there's one parameter in the model that controls the processing speed, okay, of the subject, right? So the prediction now is going to be, from the modeling perspective, the prediction will be that the latency factor should be inversely correlated to Q weighting. Now, why is that? The reason is that if you're a faster reader, then your latency factor value will be small, okay? So the faster the reader, that's the hypothesis now. The faster the reader, the more fluent you are. You might be a person who weights the C command, the principle A of the binding theory, you use that more efficiently. You might be a more efficient user of the grammatical principle C command because you're a more fluent reader. If you're less fluent, you might not be using that principle so efficiently. So you might not have higher Q weighting. So that was the underlying logic for making this, relationship, drawing out this relationship between the speed of processing and Q weighting. Okay. So that's my prediction now, right? That the latency factor should be inversely correlated to Q weighting. Now, how do we test this prediction? Okay, so I'm going to test this prediction now. So first of all, I tested it empirically. The way I did that was that what I'm showing you here is the Dylan data at the top and the replication attempt that we did at the bottom. Let's focus our mind on this figure here. Okay, so on the x-axis, I'm showing you scaled subject estimates, subject level processing speed estimates. So a positive value means a slow subject, a negative value means a fast subject. So these are scaled at the log scale. So that's why the numbers are so small. Okay? So these are slow subjects, these are fast subjects here. So we are seeing individual variation in the speed of processing of the subjects. On the y-axis, I'm showing you the magnitude of the interference effect, okay? So what you should see in the agreement dependency here is that the slower subjects have effects that get bigger and bigger. You see that they are more negative. These are also on the log scale. The slower the subject, the more negative the effect in agreement dependencies. In reflexives also, we see a slightly noisier situation. There's a very tight fit here. This is a noisier situation, but again, you see the same pattern. The slower the subject, the larger the facilitatory interference effect. And again, we see the same pattern in the reflexive replication attempt that we did. The slower the subject, right? The slower the subject here, the larger the negative effect. Okay, so we see that same pattern here, same pattern here. So this is a replicable pattern that we are seeing, that the slower subjects will show larger facilitatory interference effects. And that's what I said here. That so I reversed the story here. So it's the faster the reader, the higher the Q weighting. So remember, the higher the Q weighting, the smaller the interference effect, right? That's why I'm saying it like this. Okay. So this, what I'm showing you here now is the predictions from the model before looking at any data. So if you vary the Q weighting and you vary the latency factor, this controls the processing speed, this controls the Q weighting, and this shows you the resulting interference effect. So what you see is that the interference effects will get bigger and bigger. So it's going up, 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 up as you decrease Q weighting. If I go this way on Q weighting, the interference effect gets bigger and bigger and bigger, right? It's going negative up here, right? And then latency factor will modulate that. So that's why I'm showing you this three-dimensional figure to show you what the predictions of the model are going to be before you see any data, right? All right, so let's see what happens now when we actually look at the data. So what I'm showing you now is data from 13 published studies on agreement attraction. So the subject verb agreement that I showed you at the beginning of this talk, and the reflexive data that I had shown you. Right? There are 13 published data sets. We got all the data sets. And what we did for each data set is that we computed the correlation between the latency factor and Q weighting in each data set. So this number here that you're seeing is the correlation between latency factor and Q weighting derived using hierarchical ABC, right? So we are estimating two parameters here at the individual level and then computing the correlation in each study. And now I'm showing you the posterior distribution of the correlation parameter in each study, right? So with a 95% credible interval. So what you see is that there's a lot of variation in the correlation, right? So if you look at these 13 studies, you see a lot of variation, but many of these are negative. Most of them are negative. There's one that is lying at 0, right? You should also notice that the uncertainty is very large in each of these studies, okay, of the correlation parameter, right? A very, very large uncertainty. So the reason for that large uncertainty is that most of these studies are low sample studies. This is a disease in psycholinguistics, right? We are suffering from this chronic illness in psycholinguistics that we never collect enough data, right? We have tiny amounts of data and then we draw incorrect inferences from it, okay? And so, so the reason we have so much uncertainty in this data is the low sample sizes that we are willing to, publish based on. If you look at this study here, this is the only high sample study that was ever done on this topic, right? This is from my lab, 181 subjects. Look at the tight estimates that we have here. These are the only two studies with tight correlation estimates, right? There's a reason for that. We have an appropriate sample size, okay? So what I'm showing you here is that, first of all, there's a lot of variation in the correlation, but if I do a meta-analysis over all these data, all these correlations, I compute the posterior distribution of the overall effect of correlation between latency and Q weighting. That's this dark bar here. You see this dark bar? So what we see is that the overall correlation is negative with a 95% credible interval that is pretty tightly clustered around minus 0.25, okay? So this hypothesis is actually correct. The faster the reader, the higher the Q weighting. This negative correlation is validated from these 13 studies that we have available in the literature right now, okay? All right. So, um, so this is what I just said. Most of the other studies are very severely underpowered, so it's very hard to get tight uncertainty estimates on the correlations. But the meta-analysis shows a pretty tight estimate of minus 0.22 correlation between Q weighting and latency factor, right? So what that means is that the longer the latency, the lower the Q weighting, right? So the underlying cause for weighting differences might be proficiency. This is just a speculation at this point, right? Because what I have done is right now, I've just used the average reading time of each subject to quantify their proficiency. That's not a very good way to do this, right? The best way to do this would be to get an independent measure of each subject's proficiency, estimate the latency factor for that subject based on that data, and then do the experiment on the target construction you're looking at, and use that subject's latency factor estimate to see if it correlates negatively with the Q weighting. That would be the correct way to do this, but we are not there yet because we haven't actually done such a study yet, right? So, but I want to now discuss the broader implications. We can actually test this idea more rigorously in the following way. So, one type of population that is very interesting now is L2 speakers, because L2 speakers are by definition not going to be as proficient as L1 speakers, right? So what we should find with L2 speakers that they should generally show weights, Q weighting, even in reflexives, they should show Q weighting close to 1. This should be true, right? Another implication is that among L1 speakers, if I can figure out what the proficiency level of each L1 speaker is, I should be able to see a negative correlation across speakers with Q weighting for those speakers, right? So this is a hypothesis. These are hypotheses that somebody has to test now. We'll have to do new experiments to test these, right? And this is the only way we can really validate this speculation that I have here. This is just a speculation right now, that Q weighting and latency might be negatively correlated, right? So one other broader implication of this work is that just looking at average differences, so it's not useless to look at average differences. I think it's a useful thing to do. Why? Because if you look at the model predictions, this is the Lewis physician prior predictive prediction about the agreement attraction and reflexive effect. You can compare this prediction to the observed data, and you can draw inferences about the average behavior of the model. Sure, that's a very sensible thing to do. It tells me something about the model, but what is really interesting about this model is the range of variation at the individual level that the model predicts. And that prediction can be tested from the data because we have the data, right? We tend to ignore it. When we do data analysis, we treat the individual level variation as a nuisance variable, okay? Sorry, am I out of time? Is it okay? Yeah, it's all right? I'm doing okay, right? Yeah,
Yeah.
yeah,
We
yeah.
still have time.
Yeah, so the we actually treat individual level variation when we do data analysis and modeling as a nuisance variable, right? So what I mean is that all the individual variation is stuck into this credible interval here. The width of this interval is actually encapsulating the range of individual variation, but it's hiding that variation. There's systematic variation that we are ignoring, right? So what I want to get across here is that it's important to study average differences, sure, but you have to go beyond that to understand the source of the individual variation if you want to really understand the underlying machinery that produces the predictions from the model, right? So that's a very important issue. Many people have talked about this in psycholinguistics, but nobody actually does anything about it. If you read the literature from the connectionist modelers, they repeatedly publish paper after paper saying that, oh, individual differences are so important, right? But where are the models? I mean, nobody's doing this, right? You need to actually now start looking at this stuff. So what I'm showing you now is the gain of looking at individual differences. I'm going to show you the model predictions, which are the black circles. I don't know if you can see them, black circles with credible intervals, right? The reason I have credible intervals on the predictions is because I'm doing Bayesian modeling here. So that's the big advantage. I have an uncertainty estimate for each subject in the Jaeger et al. Data. I have an uncertainty estimate of their predicted agreement attraction effect. Okay, it's a pretty decent estimate because if you compare it to the observed shrunken estimates, so these estimates in this I don't know what color this is, but it's not black. So in this color, these are the estimates from the linear mixed model, okay, that you fit to the data. Right? So that's why they're called shrunken estimates. So they are basically derived from the linear mixed model. And so what you notice is that the model predictions are very, very close to the observed data. So the model is doing an excellent job of predicting the subject's individual level effects, right? And so that's a big achievement, I think. The fact that the model can actually talk about this individual level variation and actually explain why different subjects might have different magnitudes of the effect, right? The same thing happens with reflexes, right? In the Jaeger et al. Data, you see a pretty decent fit between the shrunken estimates of the subjects and the model predictions. Okay, so the last thing I want to show you is that if you cluster the subjects such that you only look at the subjects in the Dillon data and the replication that we did, where subjects have equal Q weighting, right? So if you remember here, if I just focus on these guys here and these guys here, okay, and I look at the predicted interference effect for these guys, what we notice is something very interesting. What we notice is that pretty much all the subjects are showing negative effects, right? You're seeing negative interference effects in all these subjects, as you would expect. So this is just a sanity check, actually. This is just a sanity check showing you that when you have equal Q weighting, you're going to see the predicted negative interference effect, the facilitatory interference effect. But you should also notice something disturbing. The disturbing thing is that the uncertainty intervals on both the Dillon data and the Jaeger data are huge. Okay, this is a lot of uncertainty on each of these estimates. The reason for that is that when we do these kinds of studies, we only collect about, I think, 8 data points per condition from each subject. So there's very sparse data from each subject on each condition. So because of the sparsity of the data, we end up with wide uncertainty in these estimates, right? The reason we collect such sparse data is that we cannot subject our poor subjects to, 100 exposures of each condition. They just get exhausted trying to read those kind of sentences. We already make subjects read, I don't know, like 120 sentences in one session. That is really mind numbing, to do that kind of experiment. And so to make them read more sentences would be very hard. But the price we are paying for that is that we are getting huge uncertainty on these estimates here. Okay. So I think I'm willing to live with that because I don't want to now make my subjects suffer. But we do still learn something from this estimates, right? We do learn that we get the predicted negative effect from these subjects, although we don't get very tight uncertainty on those estimates, right? So that was the main point of my talk here. I wanted to show you the importance and advantage of looking at individual level differences. I showed you how you can use a computational model to estimate the parameters inside the model to derive the predictions at the individual level. And of course, the most important work here is the stuff I didn't talk about at all, which was the technical detail involved in computing the parameter estimates. That's where all the hard work was, right? That's all the hard work that Himanshu did to be able to do all this parameter estimation effortlessly, right? So I think that's the big achievement of this work, the methodology that we have now. So I think the next steps in this modeling are going to be the following. We actually have been, over the last 4 years, we've been developing a really fantastic data set. So one of my other students, Doro Pregla, has been collecting data from unimpaired control participants and individuals with aphasia. So what we did was we took a range of syntactic constructions, subject object relative clauses, control constructions, and pronoun antecedent constructions, and so on. And we had control subjects and individuals with aphasia who were age matched. We collected data from both these populations. And one cool thing that we did was that we brought the same people back twice. And so we made them do the same experiment twice, separated by several months. So what we have is a test retest data set from the same people with the same items, right? Same experiment, right? So what we're going to do next is that we're going to do the parameter estimates for each of these individuals, both controls and individuals with aphasia, using the first data set. And then we're going to look at the reliability of those estimates on the repeat retest data set. That will actually establish something that we cannot establish right now, whether our estimates actually reflect something stable. Our parameter estimates for the individual, do they reflect something stable about that individual or not? Or are they just a random artifact of that particular experimental, session that that subject did? So one very important question in individual differences research is whether your estimates for the subject are reliable. Are they telling you something about that person, something invariant about that person, right? So when I compute a Q weighting parameter and a latency factor parameter for that subject, am I estimating something stable about that person, or am I estimating some random number that's going to change every time that subject does that experiment, right? In one experiment, the subject might have a Q rating of 1, and another time he might have a sub Q rating of 4, right? If that's the case, then that's not a very informative number about that subject, right? So we want to understand whether this is a reliable number or not, right? Reliable estimate or not. So that's one direction that we're going to go in next. And one other interesting issue is that right now we've only looked at two parameters, the latency factor and Q weighting. But in the Lewis-Vasist model, there's actually one or two other interesting parameters that have theoretical interpretation, especially in the case of modeling brain damage, in the case of aphasia, right? So one parameter that is very interesting for us there is the noise parameter. The noise parameter actually just randomly varies the activation of items in memory. And this has an overall impact in changing how many retrieval failures you have, how many parsing failures you have in the system, right? And the reason this is interesting is that individuals with aphasia, they often show parsing failure, right? If you make them read sentences with active and passive sentences or subject versus object relative clauses, they will misinterpret the sentence, right? So they kind of have a retrieval failure or a parsing failure. And one way to model that is with a noisy system and by increasing the noise level in the model. We've done this before and published several papers on this. So what we want to do next is that we want to vary three parameters: Q weighting, latency factor, and noise, right? And this should be able to model the individual differences in the individuals with aphasia along these three dimensions in a systematic way. And we should be able to explain the range of, impairment and the type of impairment of different individuals along these different directions. So that's really exciting work that will happen in the future. We're still working on it. But I just want to point out that there's a lot of interesting implications that you can draw out when you start looking at what a model predicts about individual level behavior. One last thing I want to say is that right now I'm only looking at one model. Now, this is actually not very interesting, right? Whenever you're doing modeling, it is much more interesting to have a competing model that makes a slightly or makes different predictions than your model, right? Because then you can isolate the correct model and eliminate the incorrect one. So what I would like to be able to do is to develop a competing model that actually makes a different prediction than the Lewis-Vasist model. And then we want to do the same procedure that I did for the Lewis-Vasist model here and check which model actually outperforms the baseline model. Right? So that is some work that we have been doing. I can tell you about that some other time, but this is something that you can do at the individual level as well when modeling individual levels. Okay, so I'm pretty much done. I just want to acknowledge the sources of funding that I've got for all the work that we did here. Himanshu was funded or is being funded by the AAD. And the work on variability that I've been thinking about is actually part of a larger Sonderforschungsbereich at Potsdam on the limits of variability in language. That's part of the reason why I was so interested on this topic. So it was funded by the DFK. And of course, I've got funding from the University of Potsdam for this. And I got funding for 2 years from the Volkswagen Stiftung that gave me time to think about these problems. And so I also acknowledge funding from them. So there was a lot of money that went into this research. And this is one of the beautiful parts of Potsdam that we never get to see. Where I work is a very boring part of Potsdam, but I always show this picture to people so that they feel jealous about my being in Potsdam. So that's it. Thanks.
Thank you. This was very interesting. So I stopped the recording now, right?